Hello everyone, welcome to the second part of the tutorial of chapter 11. In this video, we will learn about ordered categorical regression. Let's begin by introducing what is ordered categorical variable. So sometimes we have outcome variables that is discrete but in which the values indicate different ordered levels. So these ordered variables should be treated differently from discrete variable or continuous variable. So this kind of ordered categorical regression actually is a mix of linear regression and categorical regression. We can think of it as a multinomial classification problem with the constraint that the categories have a certain direction. So our problem now is how to ensure that the model can map the outcome in the correct direction. So at the end, our prediction of these kind of models should be the relative probabilities of it in different levels. Like in level 1, the relative probability is 20%, in level 2, 10%, in level 3, 30%, in level 4, 5%, and so on. What we use here is from an experiment. So people with different education level are asked how much permissible that action is taken in a trolley problem under different scenarios. So the researchers of this experiment designed some different scenarios to test these three factors: action, intention, and contact. Which of these factors has a more powerful impact on the people's response to this trolley problem? It's actually very similar to the Excel pivot table function that we are interested in the distribution of different response levels regarding different combination of these factors. As an experienced data analyst, we won't just use the pivot table in Excel. We will use more advanced statistical model to estimate the parameters, take the uncertainty into consideration to gain more insights. Let's first look at the overall distribution of the 7 responses from our data and the cumulative distribution of the responses. The histogram on your left-hand side is our goal. We want to predict the different distribution of these 7 responses under different combination of the factors like intention, contact, and actions. But the key to solve this problem mathematically is on the right. By estimating these 7 intercepts on the right, well, actually just 6 intercepts because the 7th intercept is always at 100%, so we don't need to estimate this. We can convert relative probabilities using the cumulative proportion in this plot, and at the same time make sure intercepts are from low to high, from small to big. Since we are predicting the cumulative proportion of these 7 levels, we can make sure that the outcomes are in the correct direction. Now you must be wondering in your mind that how can we estimate these intercepts? Actually, we don't require any new skills. We just use the logic transformation on this cumulative proportion to convert this cumulative proportion to the real line. As you can see here, the shape of these cumulative proportion are very similar, but notice that the values on the y-axis now is the whole real number line. However, in this plot, the values on the y-axis just range from 0 to 1. And here is from like -2 to this is positive infinite. Once we've made these cumulative logic values on the real number lines, we can estimate them using the linear models. And to get the relative proportions, we just need to do these processes inversely. Like we can take the inverse logic function to convert these cumulative logic value back to the cumulative proportion like here, and then we can do subtractions to convert these values back to a relative proportion. I know you must be very confused about what I just said, but no worries. Let's dive into the math of this model and learn it in a more structured way. Firstly, we define qk, which are the intercepts of the cumulative proportions from k equal to 1 to k equal to 7. And then we define alpha k, which is the cumulative log R of the intercept. It's also from k equal to 1 to k equal to 7. And then, just like we had logit y equal to alpha plus beta times x in logistics regression, here we have logit cumulative k equal to kappa k plus beta x. We just use net minus kappa k to represent all the beta x in this model. So we will use the linear model here to estimate the parameters of different factors here. And then after having these parameters, we need to convert the cumulative logic back to the relative proportion scale. So the relative proportion for level 1, P1, will be equal to cumulative proportion Q1. And for relative proportion from P2 to P6, the relative proportion will be like cumulative k minus cumulative k minus 1. So you can see the graph here. The blue bars on this plot is the relative proportion of different levels. So the relative proportion of level 2 will be the cumulative proportion of level 2 minus level 1. And for P3, it's Q3 minus Q2. P4, it's Q4 minus Q3. For P7, it's a little bit different because we actually didn't estimate Q7. Q7 is just 1. So P7 is just 1 minus Q6. We also have this in the mass function here. You can see P capital K, which is P7, is equal to 1 minus Q6. Once we got all the relative proportions from P1 to P7, we can use the standard built-in function called categorical distribution as the sampling statement to complete our model. You may wonder why we subtract the linear part, the kappa K, from the intercept. That's because a subtraction will shift the probability to higher values. So a positive beta coefficient means a positive impact on the outcome probability value if we use the minus sign here. And then we can start to insert our data into the model. As I mentioned before, there are 3 scenarios to consider: action, intention, and contact. And all these 3 factors are binary variables, so we can also investigate in their interaction terms. So the author suggests us to look into the interaction of action and intention, this is the first pair, and the second pair, contact and intention. The author didn't include some interaction terms for his reasons. If you are interested in the topic, you can look at the textbook. The author has some explanations there. Here, I just follow the code with kind of 6 scenarios here. We need 5 parameters like beta 1, beta 2, beta 3, beta 4, and beta 5 to understand all the different effects in this model. So there are 11 parameters in total with these 5 coefficients plus the 6 intercepts as I mentioned here. So our linear model will look like this. If it's the first situation where we have no action or interaction term, kappa k here will be 0. We only have these 6 intercepts. And if we have action estimated by beta a, the effect of contact is estimated by beta c. And for intention, since there are 3 variables that are related with intention, so as you can see now, we extract intention out of the equations and make it like this. So this is the effect of intention only, and beta IA is the effect for the interaction term from action and intention. Beta IC is the interaction of contact and intention. By doing so, our model kind of look simpler. And here I make the above 6 situations into a data frame, so we can insert this data frame into our STEM model in the generated quantities block to make the predictions. So the first row is like no predictors or interaction, and the second row action only, third row contact only, fourth row intention only, and fifth row and sixth row are just like this. After solving all the difficulties we had previously, we can finally go into our STEM model. You will be surprised that the STEM model here is actually very simple. We just need 1 more parameters, the ordered cut points. Ordered is actually a special version of vector. An ordered vector has a constraint that all the values must be from small to large, which perfectly match our assumption that our cumulative proportion on the cut points must be from small to large. In the transform parameters block, I just insert the linear model I have explained. So the first row is the all things related with intention. Second row, I insert this bi into the I here. And in the model block, wow, we only need 1 function, the ordered logistic function. So we just need to insert the linear models, our yi, and the intercepts, the cut points, into this ordered logistic function. Then R will do all the conversion from a cumulative logic and back to cumulative proportion, and then back to relative proportion. All the difficult things, well, it's done in this ordered logistic building function. So actually, you don't need to worry about the difficult part, the complicated part, if you didn't understand it very well. You just need to remember this ordered logistic function. Here's the stand output of this complicated model. We can first look at the cut points. these 6 values are the cumulative logout values. So they are real numbers, and they are from small to large. We can use the inverse logic function to convert these values back to their cumulative proportion. So you can see that level 1 just 6%, level 2 12%, level 3 20, 42, 60, 80, and level 7 cumulative proportion of level 7 must be 1. So it's not listed here. You will notice that all the parameters are negative, meaning that adding any of these factors will make the situation of the trolley problem less permissible. And the effect of intention itself, it seems to be the least. However, the interaction of intention and contact is the strongest. And the next step for us is to visualize these results. Since we have 6 different scenarios, the simplest way to visualize the result is have these 6 histograms, one for each of the scenarios here. But the author come up with a smarter way, so he kind of grouped the 6 histograms here into 3 columns, and you can see there are 3 columns and with 2 colors. So here it's still we have 6 histograms, but by putting them all together, it's easier for us to compare different factors. Let me explain how I came up with this plot first, and then I will tell you what's the story behind this plot. So you can notice that the 3 columns here are representing A equal to 0, C equal to 0, A0, C1, A1, C0 respectively. And the color for blue and red are just intention being 0 or 1. So you can notice that actually I had some tricks making this data frame. So you can see I have AZ00, 1001, and here it's repeat again 00, 10, and 01. For I, the first 3 rows are all zeros, and the last 3 rows are all ones. So although the output from Stan is in a white table, firstly I use the getter function to convert this white table to a long table, and you can see we have now 12,000 rows with 2,000 rows times 6 scenarios. And then I can easily tell R which scenarios is this prediction. So for prediction, the scenario 1, A is equal to 0, C equal to 0, there are 2,000 rows. And for scenario 2, A1, C0, again 2,000 rows. Prediction third scenario, A0, C1, and 2,000 rows. And then for scenario 4, 5, 6, we can just repeat these 6,000 rows again. These are for action and contact. And for intention, well, the first 3 scenarios are all 0, and the last 3 scenarios are all 1, so 6,000 rows for both of them. After doing this, the data will look like this. Okay, so now we just need to split the 6 histograms using the facet wrap function, and then give them different colors using the fill and group function in the geometric histogram. Set the position parameters to dodge, then we will get the result like this. If you don't set the position parameters to dodge, the blue line and the red line will be in the same one, and you can't visualize the differences. And what are the stories behind this plot? You can look at this plot from many aspects. And the simplest one you can notice is that there are more blue counts in the lower levels. And if we have intention and contact at the same time, we have the highest blue counts. If you want to know the impact of contact, and you can compare these 2 columns. And if you want to know the effect of action, you can compare this column and this column. Even though it's just one graph, there are many stories behind the scene waiting for you to investigate deeper. So I would leave this graph here, and you can read the textbook to find more interesting results. Finally, we can move on to the last part of this chapter, which is about treating these kind of ordered categorical variables when they are predictors. We will use the education variable in the same dataset as our example. As you can see, there are 8 different education levels for our experiment taker. From the lowest, I guess it's elementary school, to the highest, which is the graduate degree. These kind of variables is a very special type of variable. I mean, they are actually categorical variables, but at the same time, they have some characteristics of a continuous variable. It's very common that in a questionnaire, we don't directly ask for the exact age or the annual income, something like that. We will provide some ranges to let them check the box. These are all the same situation where we can't just simply treat these different levels as from like 1 to 8 because the differences between different two levels may be different. Like we have like 6 years in elementary school and only 3 or 2 years in high school or some high school. The impact will not be the same, but we cannot treat these variables as like just different group because they are related with each other. So we will use the same technique we used in the first part. We will use a cumulative concept to deal with these ordered categorical predictor. So instead of estimating the total effect of each education level, instead we want to estimate the incremental effect of moving from elementary school to some high school, and the incremental effect from some high school to high school graduate. So the total effect of being a high school graduate will be the sum from elementary school and some high school, and the difference from some high school to high school graduate. And to make it more convenient for interpretation, we can even define the total effect of the education variable as beta E for education, and make the incremental effect like in the proportion scale. Maybe from elementary school to middle school will be a 10% increase compared with the total effect, and from middle school to some high school, it's another 10% increase, and from some high school to high school graduate, like 5% increase, something like that. By doing so, we can define the prior in a more structured way, because we no longer need to guess for the exact effect of each level. We just need to guess the distribution of the effect over different levels. So if you think that the distribution of the effect over different levels should be the same, like each increase in the education level should have a similar impact on the person, well, you can set a prior like on your right hand side, where the x-axis are the different levels from level 1 to level 7, and the y-axis is the proportion of the effect. And on the right side, you can see that all the effects are kind of uniformly distributed, like they are all around 20%. However, if you think incremental effect in different education levels should not be the same, you can set a prior like on your left-hand side. As you can see, like there are high and lows in all different levels. Or maybe you think that level 6 has a very strong effect, and for the other, the effect is small and you're not certain about that, you can set a prior like this. The coolest thing is that there is actually a distribution that can help us define the prior distribution like this. It's the Dirichlet distribution. So Dirichlet distribution is like the multinomial extension of the beta distribution. In the beta, there were only 2 parameters, and actually the 2 parameters are kind of your confidence, how much you believe like something will success or fail. If you think something will success more, and you can put higher values on the alpha. If you think it will more likely fail, and higher values on beta. Beta distribution is only for binomial outcome. But for Dirichlet distribution, we have no such limit. Like the input of a Dirichlet distribution is just a log vector. Like depends on how many outputs you have. So it will be something like this. We have 7 outputs, so the input will be a vector of length 7, and each element in the vector is like how much confidence you have for that output. So like for this one, the output is like this. So like we have low confidence on level 1, 2, 3, 4, 5, but we have high confidence on level 6, so I put a 10 here. And but for level 7, I again have low confidence, so it's another 2 here. So the result will be like this. But if you have same strong confidence on all the output, you can let the vector be something like this. You have 100 values, and the output will be like this, since you have the same confidence on all the levels, and the output will be uniformly distributed over all the levels. So by using the Dirichlet distribution, we can construct our prior distribution in a very mathematical way and a very intuitive way. After dealing with all the difficulties, now we can jump into the STEM model, which is the smallest part as well. In the data part, I add something new. There's, of course, the education predictor, and also there's a vector of 7. It's called alpha. So this is for the Dirichlet distribution. I want you to play around with the Dirichlet distribution, so I didn't set a fixed vector. You can input any combinations of alpha in your data, and it will generate different Dirichlet distribution during the sampling process, and your results will be a little bit different. In the parameters part, we have again a new data type called simplex. Simplex is another special type of vector with a constraint that the sum of the elements in a simplex vector must equal to 1. So the simplex data type perfectly match our need for the delta, which is the incremental proportional effect. The cut points here is the same cut points we had in the previous model, and something new is in the transform parameters block. Here you can see that I define a new vector called delta j, and delta j is equal to append rule 0 and delta. What does this mean? It's actually just adding the 0 into this simplex, because there are 8 levels and one of them is the reference level, so we only have 7 parameters in the simplex to be estimated. If we didn't append the 0 in front of the delta vector, we cannot use this very simple function to calculate the incremental proportional effect. If the education level for the ith row data is 1, so we will have a summation delta j from 1 to 1, which is 0. And if the education level is level 3, well, this function will calculate the summation of the delta j from 1 to 3 will be 0 plus the first incremental effect and the second incremental effect. Lastly is the model block. So we have the education effect, and I set the prior the same as the prior for the other 3 scenarios. This is the total effect. And then our delta is following a Dirichlet distribution. And you can change the Dirichlet distribution by changing the alpha as in the input. So here in my sample code, I use uniform weak prior as the Dirichlet distribution. You can change these 2 to 10 or to 100 to see the impact on our data. Here is the output from STEM. You can see that we have delta 1 to delta 7, and the sum of these proportions should equal to 1. And here you can see the effect of education. It's also negative, meaning that when people receive more education, more unwilling to pull the bar in the trolley problem. But the impact from education is not as strong as these 3 scenarios. Also, you can see that the incremental effect for most of the education levels are about the same, except for delta 5. I guess it's the 6th level of education. So we've gained much more insights than when we can only use logistic regression or linear regression to deal with this kind of ordered categorical variable. I hope you can someday apply these techniques in your research or when you are analyzing data from questionnaires, and you can investigate some new and interesting insights. This is the end of the tutorial of chapter 11. I hope you enjoy it, and we are only 2 chapters away from the end of this class.